Good morning. So before I start for today, probably in the next 3 weeks, I'll have this lecture due to your constructionarium activities. All right. I think that on 3rd of February, 10th of February, we will have these 2 hours with Ahmed for that activities preparation. And for 17th of February, you're out of the campus in that place to do those activities. So all in one, on 3rd, 10th, and 15th of February, we don't have this lecture. And unfortunately, however, as a compensation, we will have, it's not final, but we will have 2 lectures of Ahmed when you come back. So probably on 10th and 17th of March, most probably, but let's wait for that. And I will send an email to everyone clarifying this. But for now, we don't see each other for this lecture for 3 weeks. And after that, we will take, so there will be 2 weeks. That's on Friday, we will have 4 hours from 9 to 1 p.m., right? Only for this module. And I think one of those weeks, we have 2 hours in lab and 2 hours here. So until then, I'll try to mark your coursework part 1. When you come back from your activities, you will see a feedback, and also you will see the coursework brief for part 2, for the term 2. So when you come back, we can discuss the coursework brief for part 2. And also we can do some of those activities in the lab for the coursework part 2. In that week, we have the IT for this lecture. So this is what we will do in the following weeks. And today we are going to go through the matrix analysis for frames, 2D frames.
When will be the submission for the second coursework?
What for the
Submission date, deadline for this?
On the handbook. It is on the handbook. I don't remember exactly, but it is on the handbook.
I think it's mid-April.
I think so, yeah.
Yes.
Somewhere in April.
Yeah.
It's almost a few days before the start of the exam week. So it's probably the week before. Like that.
You're gonna be individual.
What do we do?
The coursework.
Yes, it is individual. Like part 1. Part 1 was individual, yeah. It doesn't make sense, a group coursework in this module at least. For example, if it's a kind of project-based module that you can split it in different parts, you can do that. But for this one, which is some sort of analysis stuff, it's very difficult to do. So today we are going to cover the matrix analysis of 2D frames, and this will be a part of the coursework as well. So today we will finish with the matrix analysis, probably, and if you remember, we have gone through the truss structures, the beam structures, and now the frame structures. That's all for matrix analysis, and that's all for all kind of static analysis. When you come back, we'll go through some methods about dynamic analysis. So this is the end. This will be the end of the static analysis. If you remember, when we had truss structures, we had truss structure the last session in 2022. Remember, in the truss structure had generally 4 degrees of freedoms, something like this. It means that if any element in the truss structure had 2 joints, every joint had the possibility to go through X and Y, right? It means that 4 degrees of freedoms for one truss element, right? So, for example, if you had a big structure with different elements with different joints, it would be easy and enough just to count your joints and just multiply your joints by 2 to come up with the degree of freedom, right? If you know the degree of freedom, you know that the structural stiffness matrix dimension. If you have, for example, if you have a structure with 5 joints, 5 nodes, it means that 5 multiplied by 2 is 10. You will work with a 10 by 10 matrix, right? When you're going through these structures. Just count the number of joints, multiply by 2, you will figure out the dimension of your matrix. So if you go back through the examples we've gone through, you will see that when you have joints, just count them, multiply by 2. Last week, we talked about beam elements. Remember? For the beam elements, how many degrees of freedoms we had for one node? Do you remember? 3, yes. Basically, it can go through X, Y, and Z. This can go through X, Y, and Z. So each node has 3 degrees of freedom, right? But for the beam, you could eliminate 2 of them because of absence of axial forces. We don't have really axial forces in beams, and we can neglect axial deformations in beams. So we can go with 2 by 2. I mean, 2 degrees of freedoms for each node. So we can eliminate this one and say, okay, we have 2 for each node. It's somehow like truss structures, but the difference is these 2 are translational deformations, but this is one translational and one rotational deformation. All right. In the beams, we have one node can go up and down perpendicular to the line of the element and can rotate. So you have a translational deformation and a theta, a rotational deformation, right? Again, if you have a structure with 5 nodes, you can just count the nodes and multiply by 2 and say, okay, we have 10 by 10 matrix when we are going to work with this example, right? However, in the frame structures, frame means it can be a combination of beam, column, etc. Right? This is the frame structure. This is a frame structure. It's a building. When you model your build with a fixed frame structure. So if you are working with your concrete or steel project, well, here you were doing something like this with ETABS, etc. When you model it in ETABS or by hand, whatever, the number of nodes you have, you can count them and multiply by what to get the degrees of freedom. So what do you think? In this case, when we have frames, how many degrees of freedom one node has? It's a kind of generalized form of the beam, isn't it? The only difference for that is we don't eliminate this one. We don't eliminate this deformation. Every node can potentially have 3 degrees of freedom, right? Every node can go through X, through Y, and through Z. This is the general form. Nothing more can be imagined. Right? What about if this structure is 3D, not 2D? This is a 3D structure. This is a 3D structure. 4 columns, 1 slab, 4 beams. This node, how many degrees of freedoms this node has?
That's 6.
Absolutely correct. It can go X, Y, Z. It can rotate X, rotate Y, rotate Z. Right? So in 3D form, we have 6 degrees of freedom in general. When we go to 2D on the screen, it's 3, because we are eliminating, really eliminating 3 of them. For example, here, we're eliminating translational deformation out of the plane, out of this surface, and we are taking this theta, but we are not taking this theta or this theta. They are 0. So this means 2D, that's 3D. Right? So the 3D is too much to be calculated by hand. We will focus on 2D. So every single frame structure you have, it's enough to count the number of nodes and multiply it by 3 to come up with the dimension of your stiffness matrix. For example, in this case, we have 1, 2, 3, 4, 5, 6. 6 nodes multiplied by 3, 18. So the matrix will be 18 by 18. However, I will eliminate some of them because of the boundary condition later. Right? But at the beginning, we're working, for example, for this one, you should work with an 18 by 18 matrix to be able to solve. So we're not going to work with 18 by 18 today, but let's see how does it work. Again, I don't go through the demonstration. I just go through the key points which we need to have to be able to solve the frame structure. Okay. And don't worry about the matrices. For the coursework, of course, you have everything on your computer. But for the final exam, whatever from these kind of analysis I ask you in a question, you will have the formulas in appendix. So if I ask something like this, I will give you this matrix. So you only need to know, when you see this matrix, you understand what it is. So you don't need to memorize it. So, if you tell me, okay, I don't know what EIL is, that's a problem. Okay? I don't know DNX prime is, that's a problem. If you see this formula, you should be able to distinguish what it is and where did you use it in the lecture. Okay? But you don't need at all to memorize any of these formulas. So, this is the stiffness matrix for one frame element. This is the stiffness matrix for one prime element, and our convention is like this. You need to have a convention to be fair to all the elements, to be consistent with all elements. Again, we are using the same convention as the truss structures and beams. For any element, you need to say, this is near end, this is far end. This is up to you. If you want to say, this is near end, this is far end, that's fine. But just you should say, this is near end, that is far end. And the arrow here goes from near end to the far end. Okay? The near end and far end definition up to you. Just say this is near end, arbitrary. This is far for each element. Okay? And when you do that, you have this arrow here, don't you? And when you have this arrow, assume that this is your x prime. I want to define the coordination system, right? When you have this arrow from near end to far end, this is your x prime axis. And this is your y prime, and this is your v prime. So in near end, we have qn x prime. What does it mean? It means force. Q means force, D means deformation. Okay. Q means force at near end along x prime direction. Right? Good morning. Q n y prime, what does it mean? It's force, kind of shear force, isn't it? Q n x prime was a kind of axial force because it is this one. This one is Q n x prime along x prime, so it's a kind of axial force, right? Q n y prime is a kind of shear force because it's shear. Means force. The node, near field, near end node, and 1 y prime. And what is this? Un z prime. Force at the near end and along the z prime. It's a kind of moment, isn't it? Right? This is axial force, this is shear force, this is moment. For these three, you have three corresponding deformation. For Qn x prime, you have dn x prime. What does it mean? It means D deformation at the near end node along the x prime axis. It means axial deformation, right? It is the deformation along y prime, which is kind of translational relational deformation, combination of deformation of node perpendicular to element length. And dn z prime is the deformation at the near end along the z prime. So at each end we have three forces and three deformations along x prime, y prime, and z. We have absolutely the same at the far end. Okay? Absolutely the same. These three are forces along x prime, y prime, and z prime at the far end. And these three are the deformation along the x prime, y prime, and z prime at the far end. right? So in each point, in each node, near node, far node, we have three forces, which means internal forces. Like I've made a section there, and they are internal forces in that node. The far end, the same. The deformations, three forces, right? And this is the stiffness matrix. What does it mean? Again, remember that it's a kind of F equal to K delta. Force, it's kind of relationship for a simple string. You remember? Force is stiffness times deformation. This is the vector of forces. These three are forces at near end, and these three are forces at far end, aren't they? These three are deformations at near end. These three are deformations at far end. These are force vector. These are deformations vector. For one element, we have 6 degrees of freedom, 3, 3. So this is 6 by 1, 6 by 1. The stiffness matrix is some sort of matrix which correlates the deformation vector to the force vector. If your deformation vector is 6 by 1, 6 by 1, it should be 6 by 6. It should be, because from the algebra, you remember, we cannot multiply any other sort of square matrix by this vector. It should be 6 by 6. If it's 6 by 6, this is 6 by 1. You multiply 6 by 6 by 6 by 1, you will get 6 by 1. The dimension which should be consistent together, right? So this is the stiffness matrix which correlates the deformation vector to the force vector for one element. Okay. To be able to fill in the stiffness matrix, you need to know A, write it here, A, E, L, I, whatever, what else? Nothing. You need to know A, section area, E, modulo of elasticity, I, second moment of area, and whatever, what else? L, length of element, right? You can make a table for each element just to be more tidy. Or you can also do something like this. You can, when you want to assemble this matrix for an element, you can, before you start, you can say, okay, AE over L is this one, 12 EI over L3 is this one, just to have them in advance, just to be ready to put in this stiffness matrix. But principally, you only need these 4 variables. Right? Any question so far? May I kindly ask everyone not to play with your cell phone during the lecture? Just kindly. Because it's just for you. For me, it's fine, but I'm pretty sure if you use your cell phone during the lecture, you will miss many points of the lecture. Just as an advice from somebody that has gone through these procedures several times. If you have about this hassle to get the train, walk, to come here, just to spend these 2 hours to learn something. It's rational. Otherwise, it's pity. It would better to be at home. Or I'm recording the lecture. That's fine. You can be watching. Right? But face-to-face teaching is something else. You can probably come up with questions, tricks. So if you have come here, please just spend these 2 hours to learn something. And I assure you, it will help you in the coursework and the final exam, etc. Right? Thank you. So, however, this is in the local coordination system, not global coordination system. It means that if I have some frame structure like this, for example, we have two columns, one beam. Lunch is on me.
Oh, lunch to me.
If you have three elements, okay, this convention is different for this one, this one. For example, if I say this is near end, this is far end, okay, the x prime is this one, right? But this one, if I say this is near end, this is far end, the x prime is this one. So the x prime, y prime, z prime is different from this element to this element. What should I do? I need to bring everything from local coordination system to a unique global coordination system. Exactly what we had done in the truss structures. Remember? In the truss structures, we did this. We do this again for frame structures. So, but still we need this stiffness matrix. We just call it stiffness matrix in the local coordination system. And we try to transform it to a unique global coordination system. The procedure is straightforward. Again, I don't go through the demonstration, I just go through final results. You can simply calculate this 6 by 6 matrix called T matrix. This is T matrix. Just a name. T. This matrix composes of lambda x and lambda y. Lambda x and lambda y are exactly the same definition that we had in the truss structures. xy minus xj over lij, xi minus xj over l, yi minus yj over l. It's kind of a sine of theta. It depends on the degree of the element comparison with your global coordinates. So don't worry about these lambda x and lambda. They are very simple to calculate. But see, it's a composition of zeros and lambda x and lambda y, nothing more. Right? So this matrix multiplies by the deformations in the global coordination system, and you will get the deformation in the local coordination system. This matrix due to this. Just to compare, multiplied by the deformation in the global coordination system, you will get the deformation of the local coordination system. This vector is what we had in the previous slide, right? That's why for the local coordination system, we write a lowercase d, everything is lowercase, and for the global coordination system, we write capital case, right? Capital D. And we have x prime in the local coordination system, we have x in the global coordination system. So our local coordination system for each element is x prime, y prime, z prime, and in the global coordination system, we have x, y, z. Right? So this transformation matrix helps us to come up with this one. This is important. The final product is this one. This is the K matrix 6 by 6 again. And this is the global the stiffness matrix in the global coordination system. We can directly use of this and forget about the rest of what I told you for now. This is a 6 by 6 matrix. And we have again those four parameters, L, I, A, E, and two more parameters, lambda x, lambda y. Nothing more, see? A, I, L, E, lambda x, and lambda y. But it looks a little bit more complicated because it has too many terms. But don't worry, all the terms are either lambda x, lambda y, or AE over L, 12 AE over L3, or
something like 6EI over L2. If you have this one, you have this here, 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 you know, you can just fill them up very quickly. This stiffness matrix is a kind of stiffness matrix which correlates the information in the global coordination system, 6 by 1 multiplied by 6 by 6 multiplied by 6 by 1. We will come up with the force vector in the global coordination system. If you want to write it, you can say like this. This is multiplied by delta, you will get F. 6 by 6 multiplied by 6 by 1 delta in the global coordination system, you will get capital F, force in global coordination system. If you didn't understand a piece of whatever I said, that's okay, because these are just formulas. We are just going to begin the tutorial example, and that's where you will get all the concepts. We are just going to use this 6 by 6 matrix, okay? Let's go to an example to see how I can implement that 6 by 6 matrix in a real example. First, let's understand what the example is. We have this structure, this is fixed, and this is probably a roller, I'm not sure. The figure is not there here. Let's check it. It is a roller. It is a roller. So how many points I have? I have a beam and a hole. How many nodes do I have? 3, yes. However, you can say, okay, I have 4 nodes. I have 1 node here, 1 node here, 1 node between, and 1 node here. That's fine. You can use 4 nodes. You can use 5 nodes. You can get here a node here, a node here, a node. Because the more nodes you get for yourself, the bigger matrix you will get. That's fine. But if you take these nodes into account, you will find the deformation exactly at this point in your matrix. But if you don't get these points in your calculation, you will have the deformation here, here, and here. And if you want the deformation somewhere between, you need to interpolate between. But if you want the deformation at a certain point in between of some element, you need to take that point into account among your points. But here, just let's go with 3 points. 1, 2, 3, at the end of both elements, beam and column. Okay? So these are node numbers. 1, 2, 3. The blue one are node numbers. And this is arbitrary based on you, whatever sequence you like. Whatever sequence you like, you're more than welcome to number your nodes. 1, 2, 3. This is element number 1, and this is element number 2. And this arrow means I am assuming number 1 is near end, number 2 is far end for this beam element, element number 1. Pay attention to the arrow. When this arrow like this means I'm assuming number 1 is near end, number 2 is far end. When I'm saying this is my arrow, it means that I'm assuming number 2 is near end, number 3 is far end. Okay? So, how many degrees of freedoms we have? we have in general, the degrees of freedoms, as I said, is number of nodes multiplied by 3. Number of nodes multiplied by 3, because each node has 3 degrees of freedom, right? So we have 3 nodes, 1, 2, 3, the blue one. 3 nodes multiplied by 3, it's 9. I should anticipate a matrix 9 by 9 before eliminating the boundary conditions. I should anticipate to work with a 9 by 9 matrix here. Okay. Wait. I need to assemble the stiffness matrix for each element. I'm going to use this formula for each element. Element number 1, element number 2. This one. I'm going to use this one. Because of that, I need to know I, E, A, L, lambda X, and lambda Y. Okay. We have, see the definition here. We have A equal to 6,000. I is here. E is here. And L is from the, this is L1 and this is L2, element number 1 and 2. So we have, basically we have 4 parameters we need. E, I, A, and L for each element. So for example, for both elements, the length is the same, 6 meters. So for both elements, AE over L is this one, 12 EI over L3, and this. God. Let's go first. Go. Okay. For both elements, these are the same. AE over L, 12 EI over L3, and 6 EI over L2. If it's not the same, we will calculate them individually for each element. Okay? Because I need these terms to put in that 6 by 6 matrix for each element, right? So I'm going to do that for each element, for element number 1 or element number 2, just to use those values to fill up in this 6 by 6 matrix. For each element, we are working with 6 by 6. When we come up with the whole elements, for whole structure, we'll see a 9 by 9. Okay? For each element, it's 6 by 6. I'm going to fill this matrix for each element. Okay?
So we'll have 2 6 by 6.
Yeah, 2 6 by 6, absolutely. 2 6 by 6 for each element, for element number 1 and 2. And then we will combine these together to come up with 9 by 9 matrix. So before I continue, the last, not least, I have, see here, I have node number, I numbered my nodes, 1, 2, 3, I numbered my elements. I put these arrows to be clear which one is near and which one is far end. And the last thing you need to do to number your degrees of freedoms. We said we have 3 nodes, multiplied by 3, 9. 9 degrees of freedoms, just number them, okay? And this is arbitrary based on you as well. See, 1, 2, 3, 1, 2, 3, 5, 6, 7. Where's 7?
7 is down to fixed 4.
1, 2, 3, 5, 6, 7, 8, 9. Where's 4?
4 is the arrow.
This should be here. This is 4. And a little bit with the arrow. It doesn't do anything with the arrow. this for this arrow, this one. Okay. And be careful, here it's not arbitrary, be careful. When, for example, for element number 1, when this is near end, this is far end, okay, the x prime is this. You need to put one like this, you cannot put one like this. Why? Because of this convention. We accepted the convention here. When we have an individual element, near and far end, this arrow shows the x prime, and this is your positive direction. This is your positive direction. These are your positive direction. These are your positive direction. You should follow this rule when you are numbering your degrees of freedoms. For beam element, the x prime is this one. So 1, 4 are along the x1, x prime, and 2 and 6 are along y prime, and 3 and 5 are along the theta, right? For element number 2, connects 2 to 3, near end to far end. X prime is like this, okay? When x prime is like this one, it means that it's wrong. The book is wrong. This should be like this. The x prime is like this.
Yeah, the arrows is going up.
Yeah, this is wrong. The book is wrong here. 2, 8. Okay. 2, 8. If it's like this, 2 and 8. This is y prime. 7 and 7 and 1. Let's change 1 because of that one. We need the beam element. If I say this is y prime, it should be y prime. And if it's 1 and 7, this is x prime, this is 3, and this is 1. Because it always goes from x prime to y prime to define the z prime. You know? But I need to check the book. I think something is wrong in the definition of those, but forget about the directions. I will clarify that for you. Okay, just go through the formulations. Okay, I'm going to fill up that 6 by 6 matrix. How? Like this. For element number 1 is here. Member number 1. For member number 1, and also you need a global coordination system which the originates at node number 1. This is X and Y. This is the global coordination system. Okay. So for element number 1, we need a 6 by 6 matrix like this. How we fill it up? We need lambda X and lambda Y. Lambda X is for element number 1. It should be X far end minus X near end over L. X far end, element number 1 is this one. X far end is number 2 here, 6 meters minus 0 divided by 6 meters. Lambda y is y far end minus y near end over L. It means for element number 1, it's 0 minus 0. Y for these two nodes are 0. See here, this is y-axis. The y here is 0, here is 0. 0 minus 0 over 6 meter is 0. So you have lambda x and lambda y. When you have 0 for some or both of your lambdas, it's a good thing because many of the terms in the stiffness matrix will be 0 and it's more simple somehow. So I'm putting lambda x, lambda y, and L, I, A, and E into the 6 by 6 matrix to come up with this one. Okay? Let's for now go with the degrees of freedoms that the book has defined. When we come up with this 6 by 6 matrix, okay, when we come up with this, these are a hint for myself. These are hints for myself. How they do they work? Like, because this is a 6 by 6 matrix for every number 1, okay? I start with the near node and the far node, near end and the far end. Near end is here. What are the degrees of freedoms? 4, 6, 5. Go for X, Y, Z. Again, 1, 2, 3. These 3, 4, 6, 5 are the 3 degrees of freedoms at the near end. 1, 2, 3 are the three degrees of freedom at the far end. I just copied this here as a column, just to be a hint for myself what degrees of freedoms are associated with this element. Okay? Once more? Or do everyone know what are they?
You can place the ROS as well, right? So that we're instead of 1, 4, 5, 4, 6, 5, 1, 2, 3, 4. 6,
No, because these are for near end, these are for far end. You should go for near end, far end.
Now, if you switch the numbers, so if you make that node.
Yes, yes, yes. If you switch the numbers, yes. We do the same for element number 2. We do exactly the same for element number 2. Number 2 is here. Again, we need to calculate lambda x and lambda y. For element number 2, lambda x is x far end. Let's call it x. It's like this. X far end is x3 minus x2 over L. X3 is 6 meter, X2 is 6 meter, X is this one, right? Origin of X is here. This is Y3 minus Y2. Y2 is 0, Y is this here, the origin is here, Y2 is 0, Y3 is minus 6 meter, because Y is positive here, negative here, right? Y here is minus 6. Is it clear? If I have lambda x, lambda y, I have also EILA. I can fill it up again for element number 2 to come up with K2. For element number 2, we need to go for these 3 degrees of freedoms, 1, 2, 3, and for the far end, 7, 8, 9. These are for near end. These are for far end. In this case, let's assume the near ends and far ends are correct for now. The near end is element node number 1. The far end is node number 2. The far end is node number 3. Right? For the column. So we have K1 and K2. We have our hints here just to see which degrees of freedoms then those numbers are associated with. And we want to combine these two to come up with the stiffness matrix of the whole structure, right? Next step. Question.
You know the first matrix, there's minus 200 on one. Where did that 200 come from?
Okay, good question. We are filling here. It should come from this term. Okay? This is AE over L, lambda x2 plus 12 EI over L3, lambda y squared. Okay? Let's see. It should be lambda y is 0. Okay? So the second term is 0. Only the first term. The first term is AE over L, lambda x powered by 2. Okay? What is AE over L? It is 200,000 kilonewton per meter. Okay? Multiplied by lambda x is 1. Powered by 2 is still 1. Okay? So it should be 200,000 multiplied by 1. So it is 200,000. 1,000 is here. 200 is here. Right? Likewise for the rest. So many of them are 0 because of lambda y. Because lambda y is 0, many terms are 0. So what we do now we have the stiffness matrix 6 by 6 for all the elements, element number 1, element number 2. We want to combine them for the whole structure. We know in advance the whole structure stiffness matrix is 9 by 9 because we have 3 elements multiplied by 3, 9. Okay? Because we know in advance we are going to have a 9 by 9 matrix, just write a 9 by 9 matrix here full of 0. 81 elements, 0. 9, 9. Right? And start filling up this 9 by 9 matrix like we used to do that, like this. Start with this, then forward going to this. This 200 we talked about should be associated with degrees of freedom 4 and 4. Okay? Just go, this is just in sequence. 1, 2, 3, 4, 5, 6, 9. 1, 2, 3, 4, 5, 6 to 9. Just write 1, 2, 3, 4, 5, 6, 7, 8, 9. Have them in the vertical as well. So this 200, don't forget about 1,000 at the back of the matrices. Because these are the same, we just put 1,000 here, that works. We just work with the internal part of our matrices. We have 1,000, we have 1,000, we have 1,000. That's consistent. But if it was 1,000, it was 100, you could bring 110 inside and keep 100 at the outside. And put 100 here to work consistently. Okay? But now we have 1,000, 1,000, 1,000. Just work with the inside. This 200 should go to degrees of freedom 4 and 4. It goes to 4 and 4. This is that 200. Right? You should repeat this for how many times? 36 times for these numbers, because these are 6 by 6. 30, you have 36 numbers here. Generally, there are some zeros, forget about them. But principally, you have 36 numbers here, 36 numbers here, 72 numbers altogether. You need to repeat 72 times this procedure. Just to go to any number, just underline it, whatever you used to, just to be sure that I've done my duty for this number. Don't duplicate any number or don't miss any number. All right? For example, what does this -2 go? It should go to degrees of freedom 2 and 6. So it should be 2 and 6. It's here. Okay. Any cell in this 9 by 9 matrix, any cell can receive two different numbers from these this procedure. But don't worry, if you need to put two numbers in two different iterations into a single cell here, that's fine. They will add up together with their sign. It can happen here in, it can happen here in the row and column number 2. For example, this 200, let's change the color. This 200 goes to column 2, number 2 here. But it's not 200, it's 202. Why? Because in another iteration, when I was working here, 2 by 2, this 2 also goes here. So this cell receives a 2 from here, a 200 from here, altogether 202. Why? Is there any physical interpretation for this? I did the physical interpretation last week for another example in B. There is a clear interpretation when this happens. A single cell receives two different numbers from two matrices. These two matrices are from element number 1 and element number 2. The degrees of freedom, the degree of freedom number 2 is vertical deformation of node number 2. If this node wants to go up, there are two elements resisting against this movement. This element resists with its axial resistance, and element number 1 resists against this kind of deformation with the flexural deformation, the resistance. So both elements, 1 and 2, contribute to this procedure. Usually this happens in the degrees of freedoms that is associated with a degree of freedom which is between two elements. Number 2 is between, somehow it's between element number 1 and 2. So this happens for degree of freedom number 2. You want to rest? You're tired, just survive. 5-minute rest, just to have some time to grab a water or whatever. Or stretch the leg. We apply the boundary condition.
I saw this. What the midspent. I don't know what the answer is. The answer is minus 0.47. But somehow I'm not getting the answer. We get some. If you just can go quickly through the problem.
Hello. Where is it start?
Exhaust.
Goes like we
Just no,
is equivalent to this 10 or
no. It's just separate. It's just a term. I'll make it 0 at the end.
you wanna okay. Okay, that's the line.
Yeah.
Okay.
Take somewhere.
Maybe here. Let's see. You have a piece of paper. I have it. Is yours.
That's my second first.
So what do? You do have two sections from the right hand side.
Yeah, that's my second section. So that's the section you did.
It's here.
Yes, sir. I took it from the left.
This is right.
Yeah, sir, right. Yeah. You took it from the left. And my equation is here.
Okay. Why? Okay. You get this one. That's correct. You got like this. Mm. Two minus y and half a px.
I'll just expand it.
It's 1.5 p.
I think I know where I made a mistake.
This is wrong. It should be minus 5x22 plus 1.5 p minus px.
So I made a sign mistake here. This is minus plus. Okay. Which will be what you explained. I think you're going to skip this one.
Yeah, but if you have questions, that's fine.
What's the reason for separating for this one?
Because when you have a distributed
I
load,
think that's why I just mean.
we have an example today for that. We need to use the superposition. You know, what are the fixed end moments when we have some distributed loads? Yes, you can send both sides, both ends to be fixed. You will have some fixed end moments at both ends, okay? What you ever have in B, you put a fixed end moment at the B as external forces. And what you get for the A node, you will take them for the last stage and you will add them with whatever support reaction you get for point A.
What's the reason for doing that?
The reason is because you're assuming that your structure is the same as this one. With fixed end moment, okay? You have some fixed end moment here and here, okay? Each fixed end moment, whatever you apply on a support, goes through the support reaction. Assume this is support. If I push it, just Newton law says if you push it, you will get pushback. If you push a support, you will get a support reaction. Deformation occurs. Right? So these goes just to support reaction. It's like following this structure. Only we do fixed end moment here. But what you get from the analysis, you will have some deformation, whatever, you will have those reactions here. But still, you have to get.
Okay.
You have two effects, one from fixed moment at the first stage, and plus whatever you have done in your analysis to get some. Let's see if I have enough time. Maybe I will go through. The next example is something else.
Thank you.
You're welcome. So, when we assemble the whole structure matrix, which is 9 by 9, exactly like what we did in master structures and mean structures, you need to comply with the boundary condition. If you really try to inverse this 9 by 9 matrix, you will stuck with some 0 or negative value for your determinant. Matrix determinant. And it's not irreversible, this 9 by 9 matrix. And you need to comply with the boundary condition, which means that you need to go to your structure to see which supports do you have. I have support in node 3, which means that the deformation at degrees of freedom 7, 8, 9 are 0. And also a roller support at number 1, node number 1, which means the deformation along 6 is 0. Right? So 6, 5, 7, 8, 9. 4 degrees of freedoms have deformation equal to 0. What should I do? I eliminate those lines and columns in my big matrix. So this dashed line separates the matrix into two parts. It's like you have eliminated line and column 6, 7, 8, and 9. What remains for you is a kind of 5 by 5 matrix, because you had 9, you eliminated 4, you will get 5. Right? Just write these 5, this 5 by 5, and these 5 here to see what you will get. This is the vector of external forces. Everything is 0, but 20 kilonewton applied here as an external forces. It is along the degree of freedom number 1, isn't it? So I just put it here. That's why I put 20 here along the degree of freedom number 1. The rest are 0. If you had some forces for the other degrees of freedom, just simply put them in the vector, right? This is just to consider the external forces you have on your structure. And this is the deformation matrix which vector which is unknown. You want to calculate them, right? This 0 is here because just emphasizing that we don't have support settlement here. But if we have support settlement, we could have something here. Just to multiply this with settlement. If we had settlement, we need to put them here and rewrite the equations. Exactly what we did in the process structures last week. Don't forget about that. For this one, you need to inverse this and multiply it by vector of external forces. If it's k, it means that this is F, this is delta. So F is equal to k delta. So delta would be k minus 1 multiplied by F. You need to inverse k multiplied by F to come up with delta. You need to inverse this one, like in Excel or MATLAB, and multiply it by vector of forces. You will come up with the vector of unknown deformations like this. All right? In this stage, your structure is solved. In this stage, your structure is solved. You know the unknown deformations. Somehow it's over, finished. However, you might need to go for support reactions or internal forces, but every further unknowns can be calculated based on these deformations. When you know your deformations in your structure, you know whatever you further need. Right? Questions until here? So as the next step, we need to go for calculating the support reactions. Q6 to Q9 are support reactions. How we can calculate them? Exactly from those lines and columns that we eliminated before. These are the support reactions we eliminated. Right? So how to calculate them? These are this part or this part. For example, which one? Q6. Q6 is this line that I eliminated multiplied by this column. These 4 are 0, but don't worry, we have D1 to D5 now. We have all of these values, all of this vector, we have them because we have D1 to D5, right? If you put these here, these are all known. So this line multiplied by this is Q6. Q7 is this line, which I was eliminating, multiplied by the vector of deformation. Each line you multiply by the vector of deformation, you will get Q6, Q7, Q8, Q9. In terms of matrix notation, it's like multiplying this part of the elimination by this part, because this part will be multiplied by this part, which is 0. If you multiply this 4 by 5 by 5 by 1, you will get 4 by 1 and your support reaction. If you don't like the matrix notation, just go for individual calculation of Q6 is this line multiplied by this line. Right? So this is how we calculate support reactions. The last thing that we can ask to calculate is the internal forces at both nodes of a certain element. Just to, if you really know the support reactions, you may go for doing some sections to come up with those. You know, it's easy as well. But there are some rules to do it with matrix notation. But really, if you know the support reactions here, for example, You know the support reaction here and here. So it's very easy. You can just make a section here just to see what is inside. Here you can make a section here to see what you have. You know, but in terms of matrix notation, you can do that with the formula of 16.7, which we had it in here. This is the formula, and let's see what we will get from that. Q1 is the forces for element number 1. K1 transpose means transpose of K1. That's 6 by 6 specifically for element number 1. Okay. Q1 is this one. K1, sorry. But it's transpose. Transpose means you just need to swap the lines with the columns. Line 1 goes for column 1, line 2 goes for column 2, line 3 goes for column 3. Transpose of a matrix means swapping the lines and columns. T1 means the transformation matrix for element number 1. That matrix which had lambda x and lambda y. This is this one, 6 by 6. Only you have lambda x and lambda y. Goes here. This is the T matrix, transformation matrix. And D is the deformation matrix. We just calculated it, right? We just calculated it, but you need to pick some of the deformation associated with element number 1. Because element number 1 has the deformation of, see, 4, 6, 5, 4, 6, 5, and 1, 2, 3, 1, 2, 3, right? We just get those deformation which is associated with element number 1. Because element number 1 has these and these degrees of freedom. 4, 5, 6, 4, 6, 4, 4, 6, 5, 1, 2, 3. In order, X, Y, Z, X, Y, Z. 4, 6, 5, 1, 2, 3. So again, 4, 6, 5, 1, 2, 3, associated with element number 1, right? So if you multiply we have all of them together. We have transformation matrix, we have the local coordination system, stiffness matrix, we have the deformation, we just calculated them. If you multiply them together, you will come up with the forces at near end and far end for element number 1. These three are at near end, these three are at far end. If you do the section, you should come up with the same results. Right? You can show the free body diagram like this as well for the elements. This is for beam, this is for column. The forces at both ends. Right? So these are the same as the fixed support reactions as well. The bottom of the column, aren't they? Right? Really nothing else we can ask to calculate. We have calculated the unknown deformations, we have calculated the support reactions, we have calculated internal forces. The only thing I can imagine and think of to be asked is some internal forces, not at both end of the elements, at somewhere between. What is the internal forces at 1/3 of that element? So just you have the forces at both elements, you need to make a section at between to get the results, like structural mechanics, like we had done in the previous lectures. But if you insist in this method, if you insist to have them in a matrix notation, you needed to make them some nodes there that you are interested to calculate those information in the first place. So it will trigger your stiffness matrix somehow. So it's a kind of, you need to compromise. If you want to add some points, you will get some more bigger matrix, but that's fine. If you do that, you will get exactly those numbers in your calculations when you go working with a stiffness matrices, right? Any questions so far? This is the next example you asked about the question. We have distributed load here, right? This is another example. Again, we have two elements, 3 nodes. Again, you will come up with some sort of 9x9 matrix, right? But the only difference of this structure with the previous one is a distributed load on this element. So what we talked about the matrices, F equal to K delta. F is external forces and delta is deformation at nodes. We really are able to enter external forces when they are concentrated on the points that we define as points in our calculation. If really we have, for example, one node here, and we should define this as a node to be able to put that force into our calculation in the matrix. But if we don't have a deformation for a node, we will not have a force in our force to put that load in. So if you have some load here, you need to say, okay, this is node number 1, 2, 3, 4. This is how it works, for example. But apart from that, if we have a distributed load, we cannot put infinity loads there just to calculate the distributed load into account. We have probably 2 options. We can make an approximation like defining 10 nodes along the element and just put every piece of that distributed load in the associated node. Just divide the distributed load into 10 parts, put each segment in one node, and you will have some sort of element like my structure would be like this, 10 individual concentrated nodes. This is an approximation, and this will significantly increase your stiffness matrix dimension as it is not desirable at all. You will come up with 100 by 100 stiffness matrix, which is work here. So another solution is to use the superposition principle, which means that we assume that this structure is identical to this structure. 50 kilonewton per meter. This is also fixed. We fix everywhere. We fix all of the nodes. Are they identical? It's a lie. They are not identical. But I will do something for them to make them identical. It's a technique like what we did for indeterminate structures. We said these are identical. No, but we do some condition. We comply with some condition to make them identical. And that helped us to solve those kind of structures. Do you remember? So we just fixed this between node, this node, but I know these are not identical. Listen carefully. What happens in this structure? This distributed load produces 2 sets of fixed end moments here and here. You had fixed end moments in some other methods like moment distribution method. Do you remember? You had fixed end moments. For example, it means that for a certain beam, two ends are fixed, a distributed load or whatever load, you have a table for different kind of load. There are some fixed end moments at left and right. You can use the table just to come up with what are the fixed end moments if you don't want to calculate them by yourself. So in every single structure analysis book, you will find a table describing the fixed end moments for different types of loading. So the question is, can I remove this distributed load and replace it with two sets of fixed end moments? The answer is yes. The fixed end moments are resultant from that distributed load. So forget about those distributed load, and I substitute this distributed load with two sets of fixed end moments. Okay? Set number left, set number right. Okay? This support here means I'm grabbing this point with my hand tightly, not to move and not to rotate. Okay, I'm just holding it. Now I'm holding it, and we have two sets of fixed moments. One here goes to the support reaction. Whatever you push your support goes to the support reaction. This is the Newton law. If I push this wall, it pushes back to me. Right? This set goes to the wall and transforms to the support reaction. But this is what I'm tolerating with. I'm just holding it, okay? I slowly try to release my hand. I slowly try to release my hand. It means that it's like that these set of left fixed moments are some sort of external loads applying on this point. Like whatever I was tolerating here, it's like I'm a support. I had some support reactions. When I'm not there, those support reactions are applied on this structure. Right? It means that this is really identical to a structure without that distributed load, but with some fixed moment external forces on this point, plus some reactions here. These reactions, just forget about them, they are here as some reactions for this support. I need to analyze this structure based on these concentrated loads on that point, which is the left resultant of the fixed moments. You don't need to deal anymore with the distributed load. You need only deal with these three concentrated loads coming from the fixed moment of that distributed load. So you need to solve your structure based on only the fixed moment. This 150 is a fixed moment. This 150 and the moment is a fixed moment. We have two fixed moments because there is no axial force, because it's a vertical load, no axial force. We have only one, like shear, and one moment. So I just calculate, solve analysis, this structure based on this 150, 150. Whatever you get for this analysis is your answer despite for this support. For this support, the support reactions are whatever you get from this analysis plus whatever you had from fixed moments. Add them together with their signs. No.
Not really.
Not really. It is not clear. How did you understand the moment distribution in last year? Just follow the procedure. The moment distribution method relies on this superposition concept. If you do not know this, how did you use moment distribution? Again.
Didn't moment distribution for
Only beam?
only beam.
Again, this is for beam as well, because if you have a distributed load for a continuous beam, the same concept is like this. It doesn't matter if I have a column here or not. Only need to have a more than a simple beam, a continuous two-based beam, continuous beam, for example. Still, I need to deal with this problem.
Hold it. Hang on.
Which part was not clear?
I understand the moment part, the fixed, but for the other side, for the fixed side, on the left-hand side, on the right-hand side, I mean. You mean like I have to add fixed end moment and the reflection, right?
Yeah. I mean, I had two sets of fixed moments, one left, one right. The left one goes here to analyze the structure. The right one, just keep them beside, okay? When you analyze your structure, at the end, just add them to what you have got with this support, right? They are there. For example, you have a cantilever, this structure, like here. Okay. Question. I push this support. What happens? Can I analyze this structure without this pushing and just keep it to the end? Yes, I can.
Okay.
But this push doesn't produce any deflection in this beam. This is just applied to the support. See, this is a wall. Okay, this is a wall. If I push this wall, nothing happens. It just pushes back. If you put a force on a support, nothing happens in the structure. Just you have a support reaction locally there. Pushes back you. It's the Newton law. Nothing happens. This is not from the P, I'm pushing the support. If you push support like this, if you push support like this, anything happens in the beam? No. In the beam happens if you have some loading on the beam, like P. P can make some deformation on your beam. But these cannot do anything on your beam. It's right here. I just fix it here, I'm holding it. Apply the distributed load. Applying the distributed load is equal to having two sets of fixed moment, left and right. Forget about the distributed load. We have a left fixed moment, a right fixed moment. The right fixed moment goes to the support, doesn't do anything with the structure because of this reason. The left one, I am holding it. This is what my hands are tolerating, right? This is a kind of virtual support I'm virtually making here. If I release it, it's like I'm applying this left fixed moment forces by my hand on the structure at this point. So it's a kind of external load, concentrated on that one. So analyze your structure for only this left fixed moments, like you have done for the previous cases, nothing different. At the end, just remember you had some extra support reaction for this because you pushed the support in the first place. You pushed the support in the first place because of the right fixed moment. You have some other support reactions because you analyze your structure for this kind of load. Just add them together. Right? This is how we transform the distributed load to concentrated load, just prohibiting us to add more nodes and have bigger dimension for our matrix.
Makes sense now.
Makes sense? Good. Still think of it, that's fine. If you have any problem, we can discuss more. That's totally fine. And we can go through the whole procedure to see how does it work. So it's open if you want. So whatever we do here is exactly the same as what we have done for the previous case. We have 3 nodes, we have 2 elements, we have 9 degrees of freedoms. Just now, because the lengths of 2 elements are different, we need to say for element number 1, we have these parameters. Just to be more quick, AE over L, this term, this term, this term. We need this term to fill in that 6x6 stiffness matrix. But if you don't like to do this, just straightforward go to the 6x6 matrix without calculating this. But these are repeating in that matrix. So if I have them in advance, it's kind of advantage just to be more quick and less human error. So I just go through the same procedure. K1 is this one for 6 degrees of freedom. We go K2 is this one for 6 degrees of freedom. Again, we have 9 by 9 matrix full of 0, just to put them in the right places, This is the vector of external forces. We have 3 external forces. These are fixed moment. This is the axial force. These are 150 coming from left fixed moments. These are the support reactions. We will eliminate them. So this is coming from feeding of these 2 into the 9 by 9 matrix. And these are 3 unknown deformations. These are 6 known deformations from supports. We have 2 fixed supports, don't we? See, we have a fixed support here and here. So 6 lines and columns will be eliminated. We have only 3 unknown deformations here to be calculated, right? So if we go and eliminate, hold this part and hold this part, we will come up with this part, this 3 by 3 and these 3 by 3 deformations. So we need to calculate D1, 2, 3. And this means we don't have a settlement. And this would be the deformations after I inverse this, multiply by this, come up with D1, 2, 3. The structure is solved here, but we need to go for support reactions, for example. If we go for support reactions, we need to calculate these 6 here. So every line multiplied by the deformations, you will get support reactions from here, right? When you get support reactions, Q4, 5, 6, and 7, 8, 9. Okay? Take a look at the picture of the structure. We have it here. So 4, 5, 6 are from here. That's fine. Those 4, 5, 6 are from here. For 4, 7, 8, 9, just take a look at them. We have something in the first place. We want to add them together. Just need to, these 3 are for that support we're talking about. So these are for the elements. The 179, 26, 59. It's rounded here. These 3 are those 179, 59. I think these 3 are in there. 27. Yes. 59.9 is 60. 100. 78. Yeah, it's a little bit different, but it's just from rounding. So these are coming from the analysis, what you have done from the analysis. And these are from the fixed moment from the right-hand side. If you add these together, you will get this one. And in fact, the final support reactions and that support the right-hand side are these numbers. Right? There's just a few difference from this one on the last slide. It's just coming from the rounding errors. 178 and that's 179. This is called superposition. We're splitting our structure into different phases with different situations and then add them up together. This is called superposition principle. That's all for today. And I'll try to check the example that I just got suspicious for the first example about the sequence of algorithms. I will let you know on the Moodle about the result. For those who joined us later, I just repeat that we will not have lectures in the following weeks because of your constructionarian activities. We will have the next 2 weeks, you will have a class with Ahmed in this hour because of preparation for that. And the 3rd and 10th of February. And on 17th of February, you all are out for that activity. So for 3rd, 10th, and 17th, which means the following 3 weeks, we don't see each other, but we are in contact via the Moodle. I will put something for you on the Moodle. I will mark the coursework. I will release the report for the second semester. Just pay attention to what I sent to you. And we will come back together after your activities. And for 2 weeks, when you come back, we will have Ahmed's class after this class for compensation as well. So it means that in 2 weeks, after you come back, we will have 4 hours on Friday from 9 to 11 and 11 to 1. So the compensation, okay? We lose 3 weeks and we compensate 2 weeks. That's the deal. Right? We should compensate 3 weeks, but because you're out for one week. I'm losing in this deal. And you're free, you're winning. So any question? Otherwise, good luck with your But still some confusion. We should do also conclusions. So this is. This is
3 or 4 hours. 4 hours is
When you come to a lecture, the only way to not get tired is to do his question.
I was doing it, but I can't do the second. I couldn't do the second.
enhance your.
Second was only 20 minutes. That was the first one that took enough.
It's not difficult to do. We have, yeah, we have time.
Concrete.
What I would get.
Huh? What is it? I've started, yeah, I've started,
We're not going to do
So if the assessor says 50, you can imagine it's not my decision. That's what is the best. You address, it's pity if you don't, because let me, we are on record, let me.